we're going to Google wireless tissue engineering. And we're going to click on the images. What do you see here? This is an image from Wikipedia. Tissue engineering. We have tissue architecture techniques, 3D bioprinting, decellularized organs, implantation of engineered tissue. Down here, we have engineered materials, scaffolds, transcription factors, growth factors, and mechanical stimulus. And here, we have novel cell sources. We have iPSCs, reprogrammed cells, cell culture in vitro, and bioreactor. Let's look at another image. Engineering smart hybrid tissues with built-in electronics. And this is from Science Direct. And what do you see? You have a human, isolate cells, cell differentiation, seed cells and hybrid scaffold. Here you have integrate electronics with scaffold, pristine scaffold, hybrid scaffold, incubate 3D hybrid tissue. And at the end, you have monitoring, stimulation, and drug release, electrode, and biomaterial scaffold. Here is another image. Self-powered assemblies for tissue engineering applications. And this is also from Science Direct. Let's click on the link and give it a read. It systematically summarizes the basic physical rules, underlining electrical field generations, and provide a practical guide for the designing of electrically active supramolecular assemblies. The general strategies in constructing self-powered assemblies, including TENG or PENG, useful in tissue engineering applications, are summarized. The research advances in using electrically active assemblies in the fields of bone tissue repair and regeneration, neuromodulation and injury repair, skin wound healing, and antibacterial are highlighted. Finally, current challenges and possible solutions of self-powered artificial assemblies are discussed, expecting to promote the research efforts and advance the self-powered assemblies from laboratory to clinical applications. Let's go back to the image. So like we just read, PENG and TENG, we have bone tissue engineering, skin wound healing, neuroscience, and antibacterial. Now let's look at another image. Advances in wireless, batteryless, implantable electronics for real-time, continuous physiological monitoring. Let's click the link. This article summarizes the recent advances in wireless, batteryless, implantable electronics for continuous physiological monitoring. The critical factors that affect the design of implantable electronics for biosensing are discussed. The recent progress of material research for developing various implantable devices is summarized. This article reviews various biomedical applications of implantable devices for human healthcare. This review summarizes recent progress in developing wireless, batteryless, fully implantable biomedical devices for real-time continuous physiological signal monitoring, focusing on advancing human healthcare. Design considerations such as biological constraints, energy sourcing, and wireless communication are discussed in achieving the desired performance of the devices an enhanced interface with human tissues. In addition, we review the recent achievements in materials used for developing implantable systems, emphasizing their importance in achieving multifunctionalities, biocompatibility, and hemocompatibility. The wireless, battery-less devices offer minimal invasive device insertion to the body, enabling portable health monitoring and advanced disease diagnosis. Lastly, we summarize the most recent practical applications of advanced implantable devices for human healthcare, highlighting their potential for immediate commercialization and clinical uses. And if we look at this image, we have the human body. On the left side, we have biocompatible materials, biomolecule, and intraocular. We have biological constraints, biocompatibility, size, implantation, and SAR. On the right, we have bioresorbable materials, cardiovascular, and neurological. Here is your energy source. We have wireless power transfer and energy harvesting. Yes, energy harvesting with the W band. And here we have the wireless communication, wireless data transmission, and wireless interrogation. Now let's go over here to this article, and we're going to read. New single-cell analysis tech incorporates advanced fiber optics directly into microfluidic chips. Droplet microfluidics has revolutionized single-cell analysis, crucial for genomics, drug discovery, and diagnostics. By partitioning samples into nanoliter droplets for detailed cellular analysis. Yet, its broader adoption is hindered by the complex, costly methods required for analyzing droplets' optical properties. This limitation underscores the urgent need for simpler, cost-effective optical sensing technologies to unlock the full potential of droplet microfluidics in various applications. A study published on March 12, 2024, in the Journal of Microsystems and Nanoengineering, unveils the innovative technology that enables multiplexed fluorescence and scattered detection of unprecedented single-cell resolution using on-chip fiber optics with droplet microfluidic applications. Now, what are microfluidic applications? We are going to cover that in the next episode.